So let's start introducing the forecasting methods, the quantitative forecasting methods. We're going to start with a simple one and also a popular one. It's called the naive forecasting method. So let's start with an example. Suppose we have the January sales. It was 68 unit. And you want to make a forecast for the sales in February. So if you look at this table here, in the first column we have the periods, we have January and February. In the second column we have the actual data. We have 68 sales for January, and we don't know the sales for February, and that's why we want to make a forecast for. So this is done here. What is the sale for February? Make a forecast. Well, a silly number or a naive method here would be 68. If you don't have any other information here, you would say, okay, it should be around 68, maybe a little lower, maybe a little higher, we don't know, but we're gonna go with 68. So the naive forecasting method is just going to use the previous period's actual value, and it's going to use it as the forecast for the next period. So we're going to use the actual sales in January as a forecast for sale in February. As you see, it's very simple and it's kind of naive, but that doesn't mean that it's not useful. So the naive forecasting method is a simple method that uses the single previous value of the time series as the basis for the forecast for the next period. This method can be used for a stable time series. That's a time series that doesn't have trend or seasonality. Or it can actually be used for a time series that has trends and seasonalities as well. So it's pretty flexible when and where you can use it. The other use of a time series is that, or the other reasons to like a time series naive forecasting method is that it's cost effective. It doesn't take it doesn't take much computation. It doesn't take a lot of effort. You can just use the previous value as the forecast for the next period, right? So it's very efficient. Also, it can be used as a starting point for other types of forecasting methods that are more complicated and complex. Another reason that you would like to justify the use of naive forecasting is that, okay, suppose that you have actually a complicated and complex forecasting technique. That doesn't mean that it's a good necessarily because it's complex. So what you can do is you can actually compare the accuracy level of that method, any other forecasting method, within that of the naive method, and you can use the performance or the accuracy rates of the naive forecasting method as a benchmark or as a lower bound for forecasting. So you compare any other forecasting technique's accuracy level with that of the naive. If it cannot beat the naive, then it's not a good method. The next type of methods, forecasting methods, are called the averaging methods, or sometimes also they're called the smoothing methods. Averaging or smoothing techniques work best when it's used for time series that tends to vary around an average. We're going to learn what exactly does this mean. So an averaging technique or a smoothing technique, what it does is going to smooth the variation in your data. So it's going to smooth the up and down in your data, especially the saddle one. The averaging techniques or the smoothing technique, they can handle step changes or the gradual changes in your time series. These techniques involve several of them. We're going to cover only three. Moving average method, the weighted moving average method, and the exponential smoothing method. We start with the first method in the averaging or smoothing techniques, which is called the moving average, MA. So as the name suggests, the moving average is uses average of your several previous values in your time series as a forecast for your next period. So let's explain this more. So as you see here in this formula, this is the formula for the moving average method. In this formula, f sub t is your forecast for for period t. So we are using MA sub n. That's a moving average method that uses n previous period values. So this is what it does, as you see in this formula. It's going to use the previous value, n previous values in your data. It sum them up and then divide them by n, the number of the values that you have. So it's a summation of n previous values in your time series and then divide them by n. So that's why it's called an average, the average of n previous values. And it's called moving because when you get a new data for a new period, you're gonna involve that one, the most recent one, and you're gonna drop the oldest value that you have, the oldest period that you have. So that's why it's called moving, because as new data for new periods is going to reveal to you, you're gonna add them and involve them in your data and going to remove the latest one or the oldest one that you have. So it's moving toward time. So as new data becomes available to you, you're going to have to update your forecast by adding the newest value, actual value in the data, and drop the oldest value that you have, and then recompute the average. This is going to make more sense when we do an example. So the number of points that you can use in this method, so we said it's n, moving average n. Moving average sub n. So what should be n? If you use higher value of n, that means that you're using more previous data in your time series. So these techniques, the forecast that you're gonna get using this model, it's going to be less responsive to sudden and subtle changes. On the other hand, if you use a smaller value for n, that means that you're going to use fewer data points and fewer values in your time series. It's going to make your model more sensitive and more responsive to subtle and sudden changes in your time series. So we have this table that includes these data. The first column includes the time periods, the months, January, February up to December. The next column are the actual sales for those periods. For January, February, for each time period, we have the actual sales. Next column, we want to make the prediction and forecast for. And the rest of these columns are for computing the accuracy metrics. So after we made our prediction, our forecast, we're going to compute the MAD, MSE, and MAP. So let's start with our forecast. We're going to use a 2 months moving average forecast. That means that to make a forecast, we're going to need to have the last 2 periods. So that means that the earliest that we can start is for March, because we need to have the 2 period months. So we cannot make a forecast for February because we only have January for. And we cannot make a forecast for January either because we don't have sales data before January. So let's start making forecast. So for January, it's going to be the average of the sales for February and January. So that's 10 plus 12 divided by 2, right? So sales for February plus sales for January, divide them by 2, which is the average, right? So our forecast for March is 11. Right now you can see actually all these sales values, but assume that you didn't have it. So if you didn't have it, the sales, you would say that the sales for March was, the actual sales is 13, the forecast is 11. So let's also compute the errors as well. The error for the forecast, the formula is actual value minus the forecast. I'm going to also compute the absolute value for our future computation, and also the square of error. So that's square, and also the percentage, the absolute percentage. So that's absolute error divided by the actual value of our variable. Okay, so that's 15%. Now, so we made a prediction for March. Now we want to make, and we got at the end of the March, we got the data for the actual sales by 13. So now we are in the beginning of April. We want to make a forecast for April. Assume that we don't know this value. So what we're going to use the formula, that would be the average of sales in March and February. So what we did is we added the new period, that's March, and we dropped the last period, which is January. So that's why it's called a moving average. So that would be sales for March plus sales for February divided by 2. And we're going to continue the error, computing the error, and etc. So I'm just going to copy and drag this here. Now we get a new, to make a new forecast for May. It's the same. So we're going to find the average of sales for from April and March. That's going to be our forecast for May. So I'm just going to copy and paste all of this, and it's going to automatically generate these numbers. So that's the good thing about a spreadsheet like Excel. All right. After we computed all of these forecasts and also these values, errors, etc. that we have here, we're going to compute the MAD, MSC, and MAPE. So let's start with the summation. So summation is just a summation of the absolute error. As you see here, the formula is summation of these. This is just adding up sum of all these values. 47 and 301 is the same. It's sum of just all the square errors here. And this is also the same. So then we're going to divide these sum value according to the formula by n or n minus 1. So for MAD, that's going to be sum 47 divided by n. What is n? N is the number of periods that you have made forecast for. Okay, n is not the number of the data value periods that you have. We have 12 months, so we have 12 data points. But we have made only 10 forecasts because we couldn't make a forecast for January, February. So we only have made 10 forecasts. That means that we have 10 errors here, right? So we only have 10 forecasts and 10 errors as well. So only count those. So n here is 10. So that means that our MAD is sum divided by 10, that's 4.7. MSE is 301 divided by 10 minus 1, that's the formula for MSE. It's sum divided by n minus 1, so that's divided by 9. And for the MAPE, that's sum divided by n, 25%. So this is how we compute this criteria. So the MAD, the mean absolute deviation, is 4.7, MSE is 33.4, and MAP is 25%. Class problem. Using this table, which shows the weekly sales from week 1 to 8, it only have the actual value of sales for week 1 through week 7. Use a 3-week period, moving average period, to compute forecast and fill it out the table. Also, compute the MAD, MSE, and MAP. Potential problems with the moving average method. It's good to know about these potential problems about any method, and especially the moving average method, so that you will not use this method inappropriately. Starting with the first problem. So the first problem is about the time period, the number of time periods that you would use in a moving average. N period moving average. When n is high, the number of periods that you would use in moving average. So that's the number of periods that you average out. Okay, like for example, a 3 moving average, a 3 period moving average, a 2 period moving average, a 10 period moving average. When n is high, it would make your forecast smooth. That means that it's going to smooth out all the fluctuation and variation in your data, but also it would make your forecast less responsive and less sensitive to changes in data. So that means that if there is a subtle and subtle change in the in the actual value in your system, in your business, your forecast is not quite catch that variation and change. It's going to smooth it out. It's kind of going to not completely ignore it, but it's going to undermine it. That's what it says. The next problem with the moving average method is that if your data has a trend, if there is a trend in your data, the moving average method is not a good method to use to make a forecast. It does not, the moving average does not forecast trends well. And also another thing to consider that is the moving average method requires extensive data depending on the number of periods that you have. For example, a 3 period moving average would require the last 3 periods of historical data, or a 10-month moving average would require your last 10 months period historical data. So if you don't have that data, if you don't have extensive historical data, then you cannot really use this method. The next smoothing or averaging method is called weighted moving average. So to understand this weighted moving average, let's go back to the moving average method. In moving average method, you put the same emphasis on the every period that you have. That means that every period that you use are the same important to you in the formula. What do we mean? So let's consider, for example, a 2-period moving average, for example. So suppose that you want to make a forecast for period T. So according to the formula, your forecast would be the actual value from the previous period, period T minus 1, plus the actual value from 2 previous periods. So that's T minus 2. And then divided by 2. So if you look here, these two values from period T minus 1 and period T minus 2, they have the same emphasis. The coefficient is actually 1 here, right? You can consider that there is a 1 here, and there is also a 1 coefficient here. So that means that they have the same importance or same emphasis in your model. Maybe this is not a good thing in some scenarios or situation, right? for some scenarios, for example, you might consider, okay, I want to put more emphasis on the most recent data compared to the oldest data because um, the most recent data are more relatable. Like the old data are in the past, they not, for example, any more relevant or define the current situation of the system. So for that reason, you may want to put more emphasis on the newest value that you have. So that means that you want to, for example, put more emphasis here than this value. So you want to pick the newest value, the newest period. You want to assign it a higher weight or higher emphasis. And we're going to do this by weights. That's the coefficient here. So this is star, for example. This would be a higher value than this. All right. So we will see this in an example very soon that would make it easier for you to understand. So let's move on so far. The most recent values in a time series are given more weights in computing a forecast in a weighted moving average. So the choice of weights, which we show them by W's here, so these W's are coefficients for each time period in your weighted moving average formula. The weighted moving average formula is kind of similar to the moving average formula, but every value from each period that you use has a coefficient W, specific to that period. And you pick those values or periods that are more recent, you give them a higher weights. The choice of W's here, the coefficients, are arbitrary. So you have to find those values by trial and error. We're going to see an example here. So when should you use a weighted moving average compared to a moving average method? Unlike the moving average that it wouldn't be able to forecast trends well, a weighted moving average can handle trends. So that's a good thing about the weighted moving average. Another note to use the weighted moving average or reason to use the weighted moving average is that if you are in a situation that you want to put more emphasis on your most recent data, that your most recent periods are more important to you than compared to the older period or older data, then you would want to use a weighted moving average, not a moving average. The weighted moving average formula. This is the weighted moving average formula here. F sub t plus 1, that is your forecast for period t plus 1. Suppose we are in period t, so that's your forecast for next period. In this formula, a sub t minus 1 is a sub t minus n, and all of these are actual values for period t minus 1, and t minus n. The w's here, w sub t minus 1, w sub t minus n. These are the weights for period t minus 1, and t minus n. These are the emphases that you want to put for each period. So if you actually set the values for the weights such that they would all add up to 1, that means that you consider the weights as percentages, then you can simplify this formula to this concise, compact formula. So we have the same table and the same data here. We have the monthly sales from January to December, and we want to use a 2-month weighted moving average to make a forecast for March to December. Because it's a 2-month period, the earliest month that we can start it is March, because we need to have the previous 2 months, January and February. And for the rest of columns here, as we did before, we're gonna compute the error, absolute error, and the squared error to compute the MAD, MSE, and MAP criteria. So let's just start here. Because this is the weighting moving average, we need to have weights here. Weights for the first period and the second period. So January is the oldest period here. We want to, suppose that we want to start making a forecast. We're gonna make a forecast for March. So for March, we're gonna use February and January. February is the most recent one here, and January is the oldest one. So if we have a weight, we're gonna put the highest weight for February and the lowest weight on January. I have already decided on weights. These are values for weights. W2 is 0.6 and W1 is 0.4. So W2 is for the most recent months, which is February, and W1 is for January. Okay, so let's start working on this. So that's going to be our highest weight, which is 0.6, 0.4, the lowest weight, multiplied by sales from January. All right, January plus 0.6, the highest weight, multiplied by the sales for February, the most recent. And you don't have to divide it by anything because 0.6 and 0.4 add up to 100%, which is 1. So that's all we did. So our forecast for March is 11.2. Now we can compute the errors. So error is just going to be our real value, actual value minus our forecast. And here we can compute the absolute value of error. And here we're going to compute the squared error. So that's the squared error. And here we're going to compute the absolute error divided by the actual value. So that's going to give us the percentage error. So now suppose that we have the sales value, the actual sales for March comes in. We know that it's 13. And we want to make a forecast for April. So for April, we're going to use the two most recent periods. That means the sale for March and February. So we're going to add in the March, the most recent one, and we're going to drop the oldest one, January. So again, this is going to be 0.4 for February sales plus 0.6 for March. And I'm going to just copy these values here. And I'm going to copy actually all of these values to compute the forecast for all of the months, April through December. Now it's time to compute the summation of these. So that's going to be the summation of the absolute error here and the summation for the squared error and the summation for the percentage error. And now that we have the summation, the formula for MAD, MSE, and MAPE works like the summation divided by n or n minus 1. So for MAD, that would be the summation minus divided by the period, which is 10, because we made 10 forecasts here. For MSE, the formula is that you have to divide it by n minus 1. So we're going to divide it by 10 minus 1, which is 9. And for the MAPE, we're going to divide the summation by 10. %. So this is our forecast. We made a forecast from March to December. We computed the errors and also the MAD, MSE, and MAPE criteria. The next averaging or smoothing method is called exponential smoothing, which is a weighted average method that is based on the previous forecast plus a percentage of the forecast error that you made. So that's all you need to have. You need to have your previous forecast and the error associated with that. In exponential smoothing, weights decline exponentially, as we're going to see an example. And also, the most recent data weights the most. So that's a note to know about exponential smoothing. If you are in a situation where you need to have you need to put more emphasis and importance on the most recent data compared to previous data that you have, then exponential smoothing have that criteria. It weighs emphasizes more on the most recent data. Exponential smoothing requires a weight. It's called a smoothing constant. We show it by alpha. So alpha, the smoothing constant, is a value between 0 and 1. And it's similar to the weighted averaging method, is subjectively chosen. So you have to choose that by trial and error. And one good thing about the exponential smoothing compared to weighted moving average and the simple moving average is that you do not need to have extensive historical data. The only thing that you need to have is your previous forecast, the forecast for the previous period, and the error associated with that. That's all you need to know to move forward and make your forecast. So here is the formula for the exponential smoothing method. In this formula, f sub t is the forecast that you want to make for period t. And all you need to know is your forecast for the previous period, previous t minus 1, and the error that you made. So this is the error that you made in your forecast, ft minus 1. That's a minus 8 t minus 1 minus ft minus 1. So this is at minus 1 minus ft minus 1. So this is the error that you made in your previous forecast. That's all you need to know. And then you're gonna use this constant alpha, which is a smoothing constant, to make this formula work. It is noteworthy to consider that if your error is actually, you didn't have any error, if your previous forecast was perfect, that means that at minus 1 was equal to ft minus 1, your forecast was perfect. If this is true, then this value is going to be 0. So your forecast for the next period is exactly equal to your forecast that you made for the previous period. Let's see an example for exponential smoothing. Suppose your forecast for sales in March was 11. So you want to make a forecast for period T. The forecast for period T minus 1 was 11. So this means that this is 11 in this formula, and this is also 11, right? You want to make a forecast for period T. The actual sales for March was 13. So A T minus 1 was 13. So the only thing that we need to know is alpha, the smoothing constant. If you plug in the value for alpha in this formula, you're going to get your forecast. So let's see what would be the impact of different values for alpha. Starting with alpha equal to 5%. If you use alpha equal to 5%, then you're going to get 11.2 as your forecast. If you use, for example, 5% as a smoothing constant, and you plug it in the formula, you're going to get 12. So that's how it would change based on the smoothing constant value. But which one should you pick? Should you pick 5%? Should you pick 50%? Or should you pick any value between these, or even greater than 50% or less than 5%? Let's figure it out. The impact of different values for the smoothing constant alpha. In this chart that you see, x-axis shown the time period, and the value for your variable, whatever it is, sales, whatever, is shown in the y-axis. The actual value in your data is shown by the black color chart, as shown here. So this black color chart is showing the actual value. We have made two forecasts here using two different smoothing constant. One is 40%, alpha equal to 40%, which is shown in the blue plot here. And also one with alpha equal to 10%, the smaller value, which is shown by the red color plot here. So as you notice in these two plots, when we have high spikes, that's high variation or high fluctuation in the actual data. The prediction, the forecast that uses the higher value for alpha, that's alpha equal to 4%, 40%, that's the blue plot. Compared to the red plot, which has a smaller value of alpha, it actually fluctuates more. That means that it's more responsive to the fluctuation in your data. So that's something to consider. If the underlying average in your data is likely to change, that means that if you have highly fluctuation in your data, then choose a higher value for alpha, the smoothing constant. Otherwise, use a smaller one.